Okay, I suppose I should just start. We're doing the first dot point of Module 5, Advanced Mechanics. The first dot point is to analyze the motion of projectiles by resolving the motion into horizontal and vertical components, making these two assumptions. The first thing we have to think about is what is a projectile? A projectile is an object with only the force of gravity acting on it. So let's try some drawings out. So if we have the ground, and on the ground we have a person standing, you might think that by that definition, they could be a projectile because they have the force of gravity acting on them, pulling them down into the earth. However, you would be wrong because the ground is also pushing them up by their feet, right? Making their feet soar over time. That is the normal force, so no, they are not a projectile. If they were to throw a footy, that footy will travel in a parabola. While the ball is in the air, it is acted on by the force of gravity. And as long as we ignore air resistance, which we're going to do, then that is the only force on it, and it is a projectile. It's not any object in the air. Some objects in the air are not projectiles, such as a rocket, because yes, the rocket has the force of gravity pulling it down, but also due to its engines, it also has its own thrust propelling it forward as well. So out of all of these ones, only the ball in the air is a projectile. So the next thing we have to think about is how do we resolve the motion of a projectile into horizontal and vertical components? You can, we do this via vector analysis. If we imagine a ball, in the air being thrown in this direction with a vector that large, so that's its velocity. Let's say this is a velocity of 5 meters per second. We can resolve it into horizontal and vertical components. The horizontal component will be a horizontal line that comes out to reach the same endpoint here as our regular vector. Okay, so it's a horizontal line that goes exactly as far horizontal as our overall vector does. We have a vertical line, it works with the same rules. It will stop exactly as high as our overall vector is. So we had 5 meters per second there. We'd call that, let's get rid of the 5 at the moment, we'd actually call the black arrow the velocity, v. We would call the the horizontal velocity would be vx, being vx, x being horizontal, like a horizontal axis on a graph, and that means the vertical one would be vy. So we'd have v, vx, and vy, and we can resolve one into the other by using some trigonometry. We have our line here, which is v. We've got our horizontal component here, and if we add the vertical component to the horizontal, so use the tail of the vertical one here and draw it over here, we've got our right angled triangle because horizontal and vertical are at right angles to each other. We can then use some simple trig to work out the answers. So in this case, this is v, this is vx, and this is vy. If we know the angle at which it was thrown, let's say the angle at which it was thrown was 30 degrees. That would mean this angle here is 30 degrees. And we can use some part of trigonometry to resolve this. I'm trying to write SOHCAHTOA. I should probably type that. Here we go. Alrighty. Good. What part will we use? Well, let's assume that we have the hypotenuse. Let's say that is 5 meters per second, so we can use sine. In that case, we have, let's write in black, sine theta, sine 30 is equal to opposite over hypotenuse. Opposite, in this case, opposite the angle is Vy. So here we have Vy over hypotenuse in this case is v. All right, a little bit of rearranging. Sine theta times velocity is going to equal vy. All right, so without too much difficulty, in fact, I could write that sine theta, that's my theta, times velocity is going to equal vy. Okay, not too hard at all. I can make this look a bit more like a theta by drawing. There we go. That wasn't too hard. All right, so that's how you resolve motion into horizontal and vertical components. And the reason we do that is because it makes the maths a lot easier when we're just dealing with vertical by itself or horizontal by itself. Because this arrow, during projectile flight, this arrow changes in unpredictable ways. But the horizontal arrow and the vertical arrow change in extremely predictable ways. And I'll show you what I mean now. If we get rid of these, let's draw the path of a projectile, a nice parabola. Get my brush, a nice parabola up and down. I can draw a better parabola than that. I am using a mouse, so please forgive me. Okay, now let's say we have a ball being thrown and it falls at these different times into all these different spots. All right, now if we think about the horizontal and vertical components at each spot, at the very top of the parabola, it is only moving horizontally. There is no vertical motion at all. The vertical part is 0. That is why the parabola is completely flat up here. Okay, now at each point in time, because there's no vertical acceleration, right? The only force on the ball is gravity pulling it down. So nothing is vertical. That means that the horizontal motion is not accelerating. It means the horizontal motion is constant the whole way. So I'm going to try draw arrows of equal length um, at every spot along this parabola, right? Horizontally, because the horizontal motion is not changing. And that is really, really useful. That means that in any horizontal motion here, we can use very simple equations to work it out. It's actually just velocity equals distance over time in the horizontal direction. In the vertical direction, things are a bit different though. This one could be, this ball is being thrown up, it is going up in the air and it's coming back down and hitting the ground. Okay, and it's starting off with a very high vertical velocity, really, really large. Now, gravity, acceleration due to gravity is negative 9.8 meters per second, negative because it is downwards. This gravity is going to be reducing this velocity. So every second, 9.8 meters per second are taken off the velocity. So at this time here, this has lost some vertical velocity, so it's not as tall as the previous one. Over here, it has lost that same amount again. So what, about that much was taken off here, so we try and take that much off again. It's quite short now. Over here, there's no vertical velocity. It's taken it off. There's now nothing. So you see it gets smaller by the same amount every time. Once it's here, we can still take more velocity off it by making it negative. So now it's getting negative. And you'll notice that at this same height, these two I tried to draw these two at the same height as each other. At that height, the positive velocity here is equal to the negative velocity here. And this one's at the same height as this one over here. Its negative velocity is going to be an equally sized arrow to this arrow here. And the same at the bottom here. I won't have enough space to draw it, but its downwards arrow is going to be the same size as this upwards arrow over here. So you can see by separating them out, we get a very consistent horizontal velocity that's constant. Our vertical velocity has a constant acceleration associated with it. And having constant velocity makes the maths easy. Constant acceleration makes the maths easy. If we had changing accelerations, that would be extremely difficult to deal with mathematically. When we get to the next dot point, that'd make that almost impossible. So we've said, what is a projectile? An object in the air only has gravity on it. How do we resolve it into horizontal and vertical components? We do that with a little bit of trigonometry. And we can do it the opposite way around. If we add these two velocities together, so this velocity plus this velocity, we get an overall velocity this. So that is the overall vector at this point. look something like that. That is the velocity at that spot in time. We can split it up into horizontal, vertical, or we could combine them again into the overall velocity. So we can do that, we can do this. Now let's talk about these assumptions. So in this problem here, both of these assumptions are just helping us mathematically again. Um, this is a model of projectile motion. It is not perfect, but it is close enough to perfect to give us useful results, but also simple enough that the maths becomes easy. So let's look at the first. Um, let's look at the first assumption: a constant vertical acceleration due to gravity. That is this one here, acceleration of 9.8 meters per second. Now, at different spots on Earth, acceleration due to gravity is not exactly negative 9.8. At the equator, it's a bit smaller. At the poles, it's a bit bigger. Near large mountains, it could be a bit bigger. And so it's possible that where the projectile started and where the projectile ended could have slightly different values of acceleration if it starts um, at the equator in the ocean and then it lands near the poles on a big mountain. The gravity could be stronger, and that will affect our acceleration. And we won't be able to have a constant acceleration in our equations. Or um, more more likely, when the ball is close to the Earth, there is the downwards force of gravity, and that downwards force of gravity is stronger when it's close to Earth and weaker when it's further away from Earth. Okay, so we'd have a bigger arrow close to Earth, smaller arrow when it's further away from Earth up in the air. Now for normal projectiles, this difference is going to be extremely small, but the difference is still there. Vertical acceleration is not constant. Um, it's just very, very close to being constant on the surface of Earth. If we were talking about projectiles that were moving um, thousands of kilometers away from Earth and then and then back towards Earth, then all the equations and modeling we do are going to start to fall apart. But if you're talking about people throwing balls, guns shooting bullets, um, planes dropping things, dropping baskets or something, um, you know, someone kicking a ball, all of those things are going to pretty much have a constant vertical acceleration due to gravity. This next one is a bit more iffy. It's a zero air resistance. Now, that's obviously incorrect. There is air resistance on Earth. That is a resistance to motion as the projectile crashes into air molecules. But there's good reason to ignore it. In this model, horizontal motion, horizontal velocity is constant, and that's a really useful thing. That means that we can just use velocity equals distance over time, displacement over time. Really simple equations to model it. With air resistance, this forwards velocity would slow down as time goes on. It would not be a constant acceleration either. It would slow down faster at the beginning because it's got a higher velocity. As the velocity shrinks down this end, it would slow down less. And as I said before, changing the velocity makes things really, really tricky. Um, Now, if you throw a balloon or you throw a piece of paper or a feather, there's a lot of air resistance. Air resistance is going to affect it a lot. It's going to slow down and come to a halt, right? Throwing a balloon in the air is going to come up and it's just going to go straight down. It's not going to travel forward at all. So those are not very well modeled by these assumptions. But if you were to throw a rock, a tennis ball, a piece of metal, a ball bearing, those are all going to pretty much act in this parabola. Air resistance is not going to have much of an effect. It might limit the height a little bit, as air resistance is going to slow down the vertical velocity, and then as it travels forward, the horizontal velocity is going to shrink quite rapidly until it comes down pretty steadily. Um, yeah, which is not a very good thing. But if you throw a rock, it's not going to be as exaggerated as this is. It might just end up being, something like this. Um, Hopefully, what real life is like and what our answer is like are not too far apart from each other if we make these two assumptions. Okay, hope that made sense. Happy studying.